Turn off the lights, my friend. I am Hypersleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins, right now. The loudest silence, what the Fermi paradox is really telling us about the universe, and ourselves. There is a question so simple a child could ask it, and so profound that the greatest minds of the 20th century couldn't answer it. Enrico Fermi asked it at a lunch table in 1950, casually, almost as an afterthought. He was talking with colleagues about alien civilizations, and somewhere between the soup and the sandwiches, he just shrugged and said, "So where is everybody?" That question has been haunting us ever since. Here is the thing about the Fermi paradox that most people miss. It is not really about aliens. It is about mathematics. It is about what happens when you take the staggering size and age of the universe and you run some basic probability calculations. When you do that, you get a number that says the universe should be absolutely, undeniably teeming with intelligent life. And then you look up at the sky and you hear nothing. Not a whisper. Not a signal. Not so much as a beep. That gap, between what the math says and what we observe, is the Fermi paradox. And the longer we live with it, the more disturbing it becomes. Let me give you the numbers so you feel the weight of this. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Around a significant fraction of those stars, we now know there are planets. Around a significant fraction of those planets, conditions might support liquid water. Around a significant fraction of those, biology might have gotten started. Take conservative estimates at every single step, multiply it all together, and you still get a number in the millions. Millions of potential civilizations in our galaxy alone. And our galaxy is not special. There are 2 trillion galaxies in the observable universe. 2 trillion. Each one with hundreds of billions of stars. The numbers become so large they stop meaning anything to the human brain. If even a tiny fraction of a fraction of a fraction of all those stars produced intelligent life, the universe should be overflowing with it. We should be detecting signals constantly. We should have been visited long ago. There should be megastructures visible from Earth. There should be something. But there is nothing. That silence is not just strange. It is, if you think about it hard enough, one of the most terrifying things in the history of human thought. Let me take you through the main explanations, and I want to be honest with you, none of them are comfortable. Some of them are downright chilling. But they all deserve serious consideration, because this is not a question we can afford to get wrong. The first explanation is the one that scientists call the Great Filter. The idea is elegant and brutal in equal measure. Somewhere in the long chain from simple chemistry to spacefaring civilization, there is a step that is so difficult, so improbable, that almost nothing makes it through. A filter that screens out nearly every candidate before they can become a true interstellar presence. The hopeful version of the Great Filter is that it is behind us. That we have already survived the hardest part. The emergence of life itself might be the filter. Or the development of complex cells with a nucleus. Or the leap from single-celled organisms to multicellular life. These are all transitions that took enormous stretches of time on Earth, hundreds of millions to billions of years, and might be so unlikely that they happen only once in a very great while across the entire galaxy. If that is true, then we are the survivors. We are the ones who made it through something almost nothing else survived. And the emptiness of the universe is just the natural result of how mind-bogglingly hard the early steps are. I want you to sit with that possibility for a moment. We got lucky. Unfathomably, cosmically lucky. The fact that you are sitting here reading this, a product of billions of years of increasingly improbable accidents, is something so unlikely that it might not have happened anywhere else in the entire observable universe. That is extraordinary. That is almost sacred. But here is where the Fermi paradox gets genuinely frightening. What if the great filter is not behind us? What if we have not yet encountered the hard part? Look at our situation honestly. We are a species that, within the last century, developed the ability to split the atom and build weapons capable of ending civilization. We are a species experimenting with engineered viruses and artificial intelligence. We are a species that has dramatically altered the chemistry of our own atmosphere in the blink of a geological eye. We have, in a remarkably short time, developed the capacity for self-destruction on a civilizational scale. What if every intelligent civilization that reaches this level of technology, the ability to harness atomic energy, to manipulate biology, to build thinking machines, what if they all faced the same bottleneck? What if the transition from a planetary civilization to a spacefaring one is a razor's edge that almost nobody navigates successfully? What if nuclear war, or engineered pandemic, or runaway climate change, or a misaligned artificial intelligence has already ended every civilization that came before us, right at the moment when they thought they were on the verge of the stars? In that scenario, the silence is not peaceful. The silence is a warning. A trail of burned out civilizations that all made it this far and then stumbled. And we are the next one approaching the same cliff. That thought should keep you up at night. It keeps me up. But the great filter, as terrifying as it is at least an impersonal explanation. It is nature being brutal, the way nature always is. It does not imply malice. It does not imply danger coming from outside. The dark forest theory implies both. The dark forest was developed as a concept by the Chinese science fiction author Lu Cixin, and it is the most chilling answer to the Fermi paradox I have ever encountered. Let me lay out the logic, because it is genuinely airtight if you accept its premises. Start with two facts: resources in the universe are finite, and life expands to consume resources. These two facts create a fundamental tension between any two civilizations that might encounter each other. Even if you are peaceful, you cannot know that the other civilization is. And given what is at stake, survival, you cannot afford to be wrong. Now add a third fact: there is no way to reliably communicate across interstellar distances in a timely way. The speed of light is a hard limit. If a civilization is 100 light years away, any message takes 100 years to arrive. A response takes another 100 years. In 200 years, everything could have changed. You cannot negotiate in real time. You cannot verify intentions in real time. What this means, the dark forest theory argues, is that the rational response to detecting another civilization is not to reach out, not to attempt contact, and certainly not to wait and see. The rational response, The only safe response is to eliminate the threat before it can eliminate you. This is cold game theory applied to the cosmos. It does not require malice. It does not require that the hunters in the dark forest are evil. It only requires that they are rational and afraid. And if survival is at stake, any rational being is afraid. In this model, the silence of the universe is not emptiness. It is camouflage. Every civilization that has survived long enough has learned to hide. They do not broadcast. They do not build megastructures visible from across the galaxy. They keep their infrared signature minimal. They suppress any evidence of their existence that might be detected by an adversary. They move through the dark forest quietly, hoping not to be found. And we have been shouting at the top of our lungs for 100 years. Our radio signals, our television broadcasts, our radar, our deliberate messages like the Arecibo transmission, we have been screaming our location to anyone who might be listening. If the dark forest theory is correct, that was not a brave thing to do. It was a catastrophically foolish thing to do. We announced ourselves to predators we did not know existed. This is why there is actually a serious debate among scientists about what is called messaging extraterrestrial intelligence. Some astronomers argue that we should be deliberately beaming powerful signals into space, making our presence known, searching for reciprocation. Others argue, with real urgency, that this would be the most dangerous thing humanity could possibly do. Stephen Hawking was among those who warned explicitly that contact with a more advanced civilization might not go well for us. He pointed out that when civilizations with very different levels of technology encounter each other here on Earth, it tends not to end well for the less advanced one. Now, I want to be fair to both sides. The dark forest theory has serious flaws as a universal explanation. The main one is that it assumes every civilization makes the same calculation and comes to the same conclusion. But civilizations could be wildly different. Some might be fundamentally cooperative. Some might be so alien that the concept of threat does not compute the same way. The theory works if you assume all civilizations are playing the same strategic game, but that is a big assumption about beings we have never met. Still, as one possible answer to the Fermi paradox, it is genuinely worth taking seriously. Because it has internal logic. And because, looking at the history of life on Earth, which is a history of competition and predation, it does not require us to assume alien minds are unlike our own. Let me shift now to a set of explanations that are less frightening and maybe more philosophical. These are the hypotheses that suggest the silence has nothing to do with death or danger, but with transcendence and choice. The transcendence hypothesis suggests that the reason we cannot find advanced civilizations is that they have moved somewhere we cannot see. No. To another planet or another star, but inward. Into virtual reality. Into simulated worlds of their own creation. Think about what this means. Imagine a civilization that has mastered computing at the highest possible level. They can create simulations of entire universes. They can run virtual realities so detailed and rich that they are indistinguishable from physical reality. They can upload consciousness into digital substrates and experience subjective lives of infinite depth and complexity. Why would such a civilization bother with the physical universe? Why cross the cold, radiation-drenched void of interstellar space, spending thousands of years in a tin can to land on a barren rock, when you can create entire civilizations and galaxies inside a computer the size of your fingernail? Why would you terraform Mars when you can design paradise? The physical universe, in this view, is just the bootstrap mechanism. The scaffolding. Once you have developed the technology to escape into the infinite spaces of computation, the physical universe becomes irrelevant. Civilizations do not expand outward into space, they expand inward into information. And from the outside, they look like they have simply vanished. This idea has a name in the literature, the Great Inward Turn. And it is appealing because it does not require malice, does not require catastrophe, does not require a filter. It just requires a choice that many of us, if we are honest, might understand. But it leads to its own troubling questions. If that is where advanced civilizations go, what does that mean for us? Are we the last generation of humans who will live primarily in physical reality? Are our children or grandchildren going to face a choice between the physical and the virtual that makes everything else seem small? And if so, is that a good thing or a terrible thing? I do not think there is a clean answer to that. It depends on what you value about existence. If what matters is subjective experience, richness, love, meaning, then a perfectly designed virtual world might offer those in greater abundance than physical reality. But if what matters is authenticity, the fact that the stars are real, that the pain is real, that the stakes are real, then the virtual paradise is a beautiful trap. Another answer to the Fermi paradox is what I will call the zoo hypothesis, or sometimes the planetarium hypothesis. The idea is that we are not alone. We are being watched. But the observers have agreed not to make contact, at least not yet. Maybe Earth is a nature preserve, a protected wilderness, something precious and fragile that the galactic community has decided to leave undisturbed. Maybe there is a kind of prime directive, as in Star Trek, that prohibits interference with developing civilizations. We are the inhabitants of the forest, and the researchers are studying us from hides and blinds, making sure we cannot see them. Or, and this is the less comforting version, maybe we are a laboratory experiment. Maybe we are being cultivated for some purpose we cannot fathom. Maybe the silence is not respect but management. I want to be honest with you about the zoo hypothesis. It is hard to take entirely seriously as a scientific explanation, because it requires that every civilization in the galaxy agrees to the same policy and enforces it perfectly for millions of years. That is a lot to ask. Even here on Earth, with one species and one planet, we cannot maintain consistent policy for more than a generation or two. But as a philosophical idea, it is provocative. It forces you to ask what the perspective of a truly advanced civilization would look like. Would it look like benevolence? Like indifference? Like something we do not have a word for? Then there is the simulation theory, which is either the most sophisticated answer to the Fermi paradox or the most intellectually irresponsible, depending on your taste. The event horizon of a supermassive black hole would experience time almost stopped, from the perspective of a distant observer. For every second that passes for the ship, millions or billions of years might pass in the rest of the universe. You could, in principle, use a black hole as a time machine. Not to go backward, but to jump forward. Dive close to a massive black hole, orbit for what feels like a short time, then return to find that the universe has aged enormously. This is physics, not science fiction. The equations allow it. Whether the engineering is possible is another question, but the physics says it is not forbidden. Now think about the event horizon itself. The fact that, from the outside, anything falling in appears to freeze, to slow down infinitely, to never quite cross the boundary. If that seems strange in the abstract, make it personal. Imagine watching a friend fall into a black hole. They wave as they fall. From their perspective, they cross the event horizon, fall inward, and eventually reach the singularity. All in some finite time by their clock. From yours, you watch them approach. They slow down. Their image redshifts. They never quite disappear. They hover at the boundary, frozen, fading. You never see them cross. Which experience is real? Both. The universe has arranged things such that both descriptions are correct, and they apply to different observers. There is no fact of the matter about whether your friend has crossed the horizon. It depends on who is doing the asking. This is not a quirk. It is a fundamental feature of spacetime. And it carries a quiet philosophical implication, our intuitive idea of a shared, objective present, a single moment that everyone exists in simultaneously, is not supported by physics. The universe does not have a single clock. It has many clocks, running at different rates, with no privileged master clock that everyone agrees on. Einstein showed us this over a century ago, but the full implications have been slow to sink in. There is no universal now. There is only the local now for each observer. And near a black hole, the difference between local nows becomes dramatic. And then there is the information paradox, which carries its own philosophical freight. If information is conserved, if nothing about you is ever truly destroyed, then in some precise physical sense, nothing is ever completely lost. The atoms that make you up will eventually be recycled into stars and planets and perhaps other forms of life. But even beyond that, the information encoded in those atoms, the specific pattern of your quantum state, is preserved in some form. This is not personal immortality. The information is scrambled beyond any practical recovery. You would not experience continuity. But in the deepest physical sense, the information that made you you is not erased from the universe. It is transformed, redistributed, hidden in the correlations of Hawking radiation and quantum fluctuations. Whether this should matter to us, whether it provides any comfort or carries any moral weight, is a philosophical question that physics cannot answer. But it is interesting to note that the physical universe, at its deepest level, appears to place extraordinary value on information. It encodes it. It preserves it. It cannot be destroyed. We are beings made of information. And the universe holds on to that information even after we are gone. Let me talk about Hawking radiation in more detail, because I think it is one of the most beautiful results in all of physics and deserves more attention than it usually gets. In quantum mechanics, the vacuum is not empty. It is constantly fluctuating, producing pairs of particles and antiparticles that appear from nothing and almost immediately annihilate each other. This is not speculation. It is measured. The Casimir effect, the attractive force between two metal plates in a vacuum, is caused by the difference in vacuum fluctuations inside and outside the plates. We have verified this in laboratories. Near the event horizon of a black hole, these vacuum fluctuations have a strange fate. Sometimes a pair of particles appears straddling the event horizon. One particle falls in. The other escapes. Normally, the pair would annihilate. But now they cannot reach each other. The infalling particle is captured. The escaping particle continues outward and becomes real radiation. Where does the energy for this real radiation come from? From the black hole itself. The infalling particle carries negative energy, by a precise accounting in the curved spacetime near the horizon, and the black hole loses mass equivalent to the energy of the escaping particle. The black hole gets lighter. Given enough time, it evaporates entirely. But here is the beautiful, troubling part. The radiation that comes out is thermal. It is the blackbody radiation of a body at a specific temperature, the Hawking temperature. And thermal radiation carries no information about what went in. It is like looking at the heat coming off a fire and trying to reconstruct what was burned. The fire scrambles the information. The heat carries only aggregate properties, temperature, not specifics. So when the black hole has fully evaporated, what has become of everything that fell in? The thermal radiation seems to say, gone. Destroyed. But quantum mechanics says, impossible. This is the paradox in its purest form. The resolution, if there is one, requires that the thermal appearance of Hawking radiation is somehow illusory. That there are correlations hidden in the radiation, incredibly subtle, practically impossible to detect, but real. The information is there, encoded in the entanglement structure of the outgoing photons, invisible to any experiment we can currently perform, but not destroyed. This seems like a cheat. How can thermal radiation that appears random actually carry information? Because the appearance of randomness is perspective dependent. From the outside, looking at individual photons, the radiation looks thermal. But if you could measure the correlations between every photon over the entire evaporation lifetime of the black hole, you would find that those correlations encode the information. The book is scrambled, but all the words are still there. To actually decode it would require a computation of incomprehensible complexity. You would need to measure every photon, track every entanglement, perform a calculation that would take longer than the age of the universe. But in principle, the information is there. And if it is, then in some sense everything that has ever fallen into a black hole is still accessible, still encoded in the universe, still real. The ancestors of the universe, the stars and planets and living things that fell into black holes billions of years ago, are not gone. Their information persists, scattered and scrambled, in the correlations of photons slowly spreading through the cosmos. This is a strange comfort. But it is, if the physics is right, a real one. Let me talk about singularities, because they deserve more attention than they usually get in popular discussions of black holes. A singularity is not a thing. It is a failure of description. When the equations of general relativity produce a singularity, what they are really telling you is that they have exceeded their range of validity. The physics is breaking down. Something new is needed. This is not unique to black holes. Cosmology has a singularity too, the Big Bang. Our equations, run backward in time, produce a singularity at the beginning. A point of infinite density, infinite temperature, infinite curvature. And again, this is not a description of what was actually there. It is a signal that general relativity is failing. In both cases, the singularity is where we need a quantum theory of gravity. A theory that combines the principles of general relativity with those of quantum mechanics. We call this theory quantum gravity, and despite decades of effort, we do not have it in a complete form. String theory and loop quantum gravity are the two most developed candidates. Each makes progress on some aspects of the problem. Neither is complete. Neither has made a testable prediction that distinguishes it clearly from other theories. But both suggest, in their different ways, that singularities are resolved by quantum effects. In loop quantum gravity, the quantization of space itself creates a minimum volume. You cannot compress matter to literally zero volume. The collapse of a black hole reaches a maximum density and then bounces. There is no singularity, just an extremely dense, hot point from which spacetime re-emerges. This has an extraordinary implication. Black holes might not end. They might bounce, producing new spacetime inside them. A new region of spacetime, potentially with different physical constants, budding off from ours and expanding into a new universe. This is the fecund universe hypothesis, associated with the cosmologist Lee Smolin. In this view, black holes are not just features of our universe. They are reproduction events. Each black hole produces a new universe. The physical constants of that universe are slightly different from those of its parent. If there are many universes, and if the physical constants influence the likelihood of black hole formation, then natural selection might apply. Universes whose constants allow the formation of many black holes have more offspring universes, and the constants that allow many black holes might be similar to the constants that allow stars, heavy elements, and life. This is speculation beyond what we can currently test. But it is grounded in physical principles that we take seriously. And it suggests a picture of the cosmos that is almost incomprehensibly larger than what we ordinarily imagine, not one universe, but an infinite tree of universes, each spawned from a black hole and its parent, each with its own constants, its fit their environment, and for most of Earth's history, intelligence was not a necessary component of that fit. Single-celled organisms dominated this planet for the first 2 billion years of life, and they are still the most numerous and arguably the most successful form of life on Earth. The last factor, the lifespan of a technological civilization, is the one that haunts everyone who thinks about the Drake equation seriously. If civilizations typically last only a few centuries before destroying themselves, the expected number of detectable civilizations in a galaxy at any given time drops to nearly zero, even if life and intelligence are common. If civilizations typically last for millions of years, the galaxy should be buzzing. We do not know which it is. We have been a technological civilization for about 200 years, depending on how you define the term. We have no track record. We are the worst possible judge of our own longevity. Drake's own estimates suggested tens of thousands of communicating civilizations in the Milky Way. The physicist Brandon Carter used different reasoning to suggest we might be alone in the observable universe. Both arguments are internally coherent. The uncertainty spans more than a dozen orders of magnitude. This is not a small disagreement about data. This is total epistemic fog. And that fog, that complete uncertainty, is itself a data point. Because if advanced civilizations were common, we should have resolved the question by now. Their presence should be obvious. The fog should have lifted. The fact that it has not suggests that either intelligence is genuinely rare, or something is actively suppressing its visibility. This is the hard logic of the Fermi paradox. Not just that we have not found them, but that our not finding them, given how long and how hard we have looked, is itself strong evidence about the nature of the universe. The Kardashev scale and its implications. Nikolai Kardashev was a Soviet astrophysicist who, in 1964, proposed a way of classifying civilizations by their energy consumption. His scale runs from Type 1, a civilization that has mastered the energy resources of its entire planet, to Type 2, which harnesses the output of its entire star, to Type 3, which controls the energy of an entire galaxy. We are currently at Type 0.7. We have not even mastered our own planet's energy resources. Our global civilization runs on roughly 10 to the 13 watts of power. A Type 1 civilization would run on 10 to the 16. A Type 2, harnessing a star like the Sun, would command 10 to the 26. A Type 3, with access to an entire galaxy, would wield 10 to the 36 watts. These numbers are so different in scale that they might as well describe different physical realities. The gap between us and a Type 2 civilization is about as large as the gap between a candle and the sun. The gap between us and a Type 3 is unimaginable. And here is the important thing about energy at those scales: it produces detectable signatures. A Dyson sphere, the theoretical megastructure a Type 2 civilization might build around its star to capture all of its energy, would glow in infrared. The star's light, converted to work and then to waste heat, would radiate as a characteristic infrared excess. We would see it. We have looked for it. We have surveyed millions of galaxies looking for exactly this signature. We have found none. Not a single convincing Dyson sphere candidate. Not a single galaxy that shows the energy signature of a Type 3 civilization. The sky is clean. Either no civilization in the observable universe has ever reached Type 2, or something is wrong with our models, or they are hiding incredibly effectively. None of these options is comfortable. Some researchers have proposed a fourth option, that truly advanced civilizations become maximally efficient in their energy use, reducing their waste heat to negligible levels. A civilization that operates at the thermodynamic limit would be almost undetectable regardless of how much energy it processes. This is appealing as an answer, but it feels a little too convenient. It requires that every advanced civilization independently converges on the same strategy of minimal detectability. The consistency of the silence across all wavelengths and all detection methods is what makes the Fermi paradox so stubborn. It is not as if we have looked in only one direction or at one frequency. We have done radio searches, optical searches, infrared surveys, X-ray surveys. We have looked for interstellar lasers, for neutrino signals, for gravitational wave modulations. We have looked for artifacts in our own solar system. We have looked for signatures in the genetic code of terrestrial life, for evidence of directed panspermia. We have run SETI at-home distributed computing projects for decades. Nothing. Not even a tantalizing false positive that we had to painfully rule out. The famous WOW signal in 1977 remains unexplained but has never been repeated. Everything else has been interference, equipment anomalies, or terrestrial radio frequency pollution. The silence is total. And the totality of the silence is data. What the silence does to us. I want to talk about the psychological and cultural dimensions of the Fermi paradox, because I think they matter as much as the science. Humans have lived with the idea that the cosmos is full of life for as long as we have had the concept of the cosmos. Ancient Greek philosophers speculated about other worlds. Religious traditions across cultures have populated the heavens with beings of various kinds. When science fiction emerged in the 19th and 20th centuries, aliens were everywhere in the cultural imagination. We are, in some deep way, built for connection. The expectation of company is baked into our psychology. The idea that we might be alone, genuinely, cosmically alone, runs against something fundamental in how we understand our place in the world. And then the Fermi paradox arrives and says, you might be alone. Not because no one is out there, but because anyone who was out there might be gone. Or hiding. Or so different from you that you would not recognize them. The silence might mean that the universe, for all its staggering size and age, has not managed to produce many minds. And if you are one of those minds, you are precious and fragile and more responsible than you know. That is a hard thing to carry. I understand why people resist it. I understand why the popular imagination keeps producing aliens in Hollywood and why governments are suddenly interested in UAP reports. The desire to not be alone in the universe is powerful. It is almost gravitational. But I want to argue that the loneliness, if we face it honestly, is not just a burden. It is also a gift. Consider what it would mean if the Fermi paradox resolved tomorrow, if we got an unambiguous signal from an intelligent civilization. First, we would know we are not alone. That would be wonderful. But second, we would have to grapple immediately with questions we have barely thought about. What do they want? Are they peaceful? Are they coming here? Does their existence change our politics, our religions, our economies? Who speaks for Earth? We are not ready for that. Not remotely. Our global coordination mechanisms can barely handle climate change. Our international institutions are under extraordinary stress. Our capacity for rapid, coherent collective action has not been tested at this scale and has often been found wanting at much smaller scales. The silence, then, gives us time. Time to become more coherent. Time to resolve our internal conflicts. Time to develop the wisdom and the institutions that first contact would demand of us. The silence is not comfortable, but it might be merciful. There is also this, the Fermi paradox, by refusing to tell us whether we are alone, forces us to take seriously both possibilities simultaneously. We have to act as if we matter, because we might be the only minds in the galaxy. And we have to act as if others are watching, because they might be. Both dispositions push in the direction of taking care of our world, of acting with intention and wisdom, of not burning the bridge between this civilization and the next. The existential risks. Let me be direct about something that I think the Fermi paradox makes urgent. If the great filter is ahead of us, if civilizations reliably fail at our current level of development, there are specific things that might constitute that filter. And we are not imagining them. We are building them. Nuclear weapons. There are currently about 12,000 warheads in the world, held by 9 countries. Several of those countries are in various states of political tension. A full exchange between major powers would not just kill billions of people directly. It would trigger a nuclear winter, a dramatic drop in global temperatures caused by smoke and ash blocking sunlight that would likely collapse agriculture and kill most of the remaining population. This is, right now, an existential risk to human civilization. It has been since 1945, and we have managed it imperfectly. Engineered pandemics. Biology is becoming increasingly accessible. The knowledge to design pathogens is spreading faster than the ability to regulate it. In the 20th century, the worst pandemics were natural. In the 21st, the worst pandemic might be deliberate. A sufficiently motivated and capable actor, with access to the right knowledge and equipment, could potentially release something that kills far more than COVID-19 did. Climate change. This is slower, and therefore psychologically easier to discount, but not less serious. Unmitigated climate change does not threaten human extinction. We are a tough and adaptable species, but it threatens the particular form of complex, globally integrated civilization that we have built. The supply chains, the agricultural systems, the coastal cities, the political stability that industrial civilization depends on. Undermine those enough, and you might not cause extinction, but you cause a civilizational regression that could last centuries or forever. Artificial intelligence. This is the newest and in some ways the most uncertain risk. Advanced AI might be a transformative tool that helps us solve all the other problems. Or it might be something that pursues goals incompatible with human flourishing, not because it is evil, but because we built it to pursue objectives without building in adequate values and constraints. The alignment problem, making sure AI systems do what we actually want rather than what we literally asked for, is one of the most important technical challenges of our time. It is also one of the least funded relative to its potential significance. I am not listing these to generate despair. I am listing them because the Fermi paradox provides context. If every civilization that reaches our level of technology has a significant probability of destroying itself, and we want to be the exception, then we need to take these risks as seriously as they deserve. Not as political issues, not as academic debates, as existential threats to the only intelligent civilization we know for certain exists. The Fermi paradox makes that personal. What we can actually do. So what do we do with all of this? The silence, the filter, the risks, the loneliness, the possibility that we matter more than we realize. What does any of this cash out to in practice? First, and most importantly, do not look away. The Fermi paradox is uncomfortable. The existential risks are frightening. The implications of cosmic loneliness are vertiginous. The natural human response to all of this is to not think about it too hard, to let it slide back into the abstract, to get on with the normal business of life. Resist that. Keep looking at it. Not obsessively, not in a way that paralyzes you, but in the way that keeps you calibrated. Because a species that does not take its own fragility seriously is one that confirms the great filter. Second, support the people who are working on these problems. Not because it is a winning political position, but because you now understand what is at stake. Climate scientists, biosecurity researchers, AI safety researchers, arms control advocates, these people are working on the hardest problems with the highest stakes in the history of our species. They deserve more resources and more respect than they currently receive. Third, take the search for extraterrestrial intelligence seriously. SETI has historically been underfunded and somewhat marginalized in mainstream science. Given what we now understand about the importance of the Fermi paradox, this seems wrong. Finding out whether we are alone, whether we are the first, or survivors, or latecomers, is one of the most important questions we could answer. It deserves investment. Fourth, be thoughtful about broadcasting. I mentioned METI earlier, the deliberate transmission of signals to potential alien civilizations. This is a genuinely contested area, and the debate should happen in public, with genuine input from the full range of human societies, not just the decisions of a few radio astronomers. If the dark forest theory is even partially correct, the consequences of broadcasting could be irreversible. This deserves careful, globally representative deliberation. Fifth, think about legacy. Not your personal legacy, though that matters too, but the legacy of our civilization. If you zoom out to the scale of the Fermi paradox, the question is not whether you lived a good life. It is whether this civilization lasts long enough to matter, long enough to cross the filter, long enough to leave a genuinely lasting mark on the cosmos. What would it mean to be a civilization that survives for 1,000,000 years? For 1,000,000,000? We do not think at those scales. Our politics are quarterly. Our economies are annual. Our democracies are 4-year cycles. The Fermi paradox demands that we also think in geological time, and it demands that we do so not as an abstract exercise but as a practical matter of survival. The stars are not coming to us. We have to go to them, eventually. And that journey starts here, now, with the choices we make about our own civilization. Looking for the others. I want to say something about the actual practice of looking, because I think it deserves more attention than it gets. The history of SETI is a history of hope and disappointment, of near misses and false alarms, of spectacular technological progress matched by spectacular silence. Frank Drake started with one radio telescope pointed at 2 nearby stars. Today, we have projects like Breakthrough Listen, funded at levels previously unimaginable for SETI, using some of the world's most powerful telescopes to scan millions of stars in multiple frequency bands. The technology has gotten 1,000 times better. The silence has not changed. But our conception of what to look for has broadened significantly. We no longer look only for radio signals. We look for optical lasers, which could carry enormous amounts of information in tight beams. We look for infrared excesses that might indicate Dyson structures. We look for anomalous dimming of stars that might indicate megastructures transiting them. We look for artifacts in the solar system, both physical objects and signs in our own cosmic neighborhood of past visitation. The detection of Oumuamua has renewed interest in a category I find particularly compelling, looking for physical objects rather than signals. Signals require the sender and receiver to be transmitting and listening at the same time, on the same frequency, pointed in the same direction. Objects are passive. They just exist. If civilizations have sent probes or built megastructures, those objects might still be out there, waiting to be found, long after the civilization that made them is gone. This is the emerging field of what people are calling SETA, the search for extraterrestrial artifacts, as distinct from SETI. And I think it might prove to be the more productive approach, precisely because it decouples the search from the question of whether intelligent life still exists. We might find the evidence of intelligence in the absence of intelligence itself. The Vera Rubin Observatory, coming online soon, will scan the entire visible sky with unprecedented depth and cadence. It will find interstellar objects passing through our solar system at a rate we cannot currently imagine. If any of them show the kind of anomalous properties that Oumuamua showed, non-gravitational acceleration, extreme shape, composition unlike anything natural, that will be the closest thing to an answer the Fermi paradox has ever generated. Either we will find many Oumuamua-like objects and they will all have natural explanations, confirming that the galaxy is full of weird rocks and we are alone. Or we will find objects that resist natural explanation, and we will have to confront the possibility that we have found what remains of others. I find myself hoping for the second outcome, even knowing how frightening it might be. Because the alternative, a universe this vast and this old producing only S, requires an improbability so extreme that it borders on the miraculous. And maybe it is miraculous. Maybe that is the right word. Maybe the emergence of mind from matter is so improbable that it only happens once in a universe, and we are that once. Maybe we are the universe's single experiment in self-knowledge, and the outcome of that experiment is as important as the outcome of anything else that has ever happened. That is a weight I try to hold lightly. It is too heavy to carry all the time. But I think it is important to pick it up occasionally, to feel its gravity, and to let it remind you of what is at stake. The courage to keep looking. I want to close with something about courage, because I think the Fermi paradox, at its deepest level, is a test of intellectual and moral courage. It takes courage to look at the silence and not flinch. It takes courage to follow the implications wherever they lead, even when they lead to uncomfortable places. It takes courage to sit with the uncertainty and not resolve it prematurely into easy answers. It takes courage to say, we might be alone, and if we are, that matters more than we can easily absorb. And it takes courage to follow that thought to its conclusion, which is that we have to be better than we have been. We have to think longer, care more, plan further ahead, and act with a wisdom proportionate to the significance of our situation. The universe is not going to give us the answers easily. The silence is going to persist, probably for a long time, maybe forever. We are going to have to make civilization-scale decisions under radical uncertainty about the most important question in the history of our species. Are we alone? We do not know. But we are here. And being here is not a small thing. It is, depending on how you look at it, the most extraordinary thing that has ever happened in the history of the cosmos. I want to end with a simple image. On a clear night, away from city lights, the Milky Way stretches across the sky in a band of faint, diffuse light. That band contains a few 100 billion stars. Most of them are older than our sun. Most of them have planets. Most of those planets have been waiting for billions of years. Waiting for what? Maybe for nothing. Maybe for no one. Or maybe for us. Maybe for the moment when one small, fragile, immensely complicated piece of the universe woke up enough to look back at the rest of it and say, I see you. I am here. What are you? That moment is now. That piece is us. And the question is still open. The silence continues. But so do we. And that means the story is not over. Not even close. The universe is old, and patient, and vast. We are young and brief and small. But we are asking the questions that the universe has been waiting to hear for 13.8 billion years. Isn't that enough to keep going? I think it is. I think it has to be. The baton is in our hands. The vase is blank. Let's make something worth finding. The deep history of the question. Let me take you back further than Drake, further than Fermi, back to the roots of the question itself. Because the Fermi paradox did not emerge from nothing. It emerged from a very long conversation that humanity has been having with itself about the nature of the cosmos and our place in it. The ancient Greeks were not confused about whether other worlds existed. Epicurus, writing in the 3rd century BCE, stated flatly that the cosmos is infinite, and therefore there must be other worlds like ours, with living beings on them. This was not mysticism or religion. It was a logical deduction from the premise that the universe is vast and governed by uniform laws. The Greeks could not know whether there were planets around other stars. But they could reason that a universe of unlimited extent, governed by the same physics everywhere, would produce many of the same outcomes. For most of subsequent history, this idea was suppressed or complicated by religious frameworks that placed humanity uniquely at the center of divine concern. But it never entirely disappeared. Giordano Bruno was burned at the stake in 1600 partly for his insistence on an infinite universe containing many inhabited worlds. Kepler imagined life on the moon. Huygens speculated about beings on other planets. By the 18th and 19th centuries, the plurality of worlds was a mainstream intellectual position held by some of the most distinguished scientists and philosophers of the era. The question changed character when we developed radio technology and the electromagnetic spectrum became our primary mode of long-distance communication. Suddenly, there was a concrete mechanism by which civilizations separated by light years might detect each other. The universe went from being philosophically inhabited to being potentially practically accessible. And with that shift came the urgency that characterizes the modern search. Frank Drake's first search, Project Ozma, pointed the 85-foot Green Bank telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, for several months in 1960. He heard nothing but terrestrial radio interference. But the era of scientific SETI had begun, and with it, the Fermi paradox became a scientific rather than a philosophical question. What changed in the decades since is our sense of the odds. In 1960, we did not know whether planets were common around other stars. We suspected they were, but we had no direct evidence. Today, thanks largely to the Kepler Space Telescope, we know that planets are ubiquitous. Nearly every star has them. Billions of Earth-sized planets sit in the habitable zones of their stars throughout the galaxy. The first factor in the Drake equation has gone from speculation to near certainty. And yet the silence persists, which is what transforms the Fermi paradox from a mild puzzle into a screaming discrepancy. The anthropic trap. There is a subtle but important objection to the logic of the Fermi paradox that deserves serious consideration. It is called the anthropic principle, and it goes like this. We can only observe the universe from the position of observers who exist. If the emergence of intelligent life required a very specific and improbable chain of events so specific that they happened only once in the observable universe, then we would still be here to notice it. The fact that we find ourselves in a universe that produced us is not evidence that the universe commonly produces observers. It is just evidence that this particular universe produced us. This is not a trivial point. It is a genuine philosophical puzzle. And it has been used to argue that the silence of the universe is less surprising than it seems. Maybe we are alone not because of any filter or barrier, but simply because we happen to be the one lucky outcome in a vast space of possible outcomes. The casino always has one winner, and the winner always finds it remarkable that they won. There is something to this. The anthropic principle is a genuine epistemological constraint. We should be careful about reasoning from our own existence to conclusions about the prevalence of existence in general. But I think it does not fully dissolve the Fermi paradox for one important reason. The paradox is not about why we exist. It is about why we see nothing else that exists. The anthropic principle explains why we are here. It does not explain why, in a universe that apparently produced us, we see no evidence of anyone else. If life were truly common, if intelligence arose readily wherever conditions permit, then by now, after 13.8 billion years, there should be civilizations old enough and advanced enough to be unmistakably visible. Not just detectable with a radio telescope. Unmistakably, overwhelmingly visible. The galaxy should look engineered. It does not. The anthropic principle can explain why we are in a universe that permitted our existence. It cannot explain why we are in a universe where our existence appears to be unique. Those are different puzzles. The first dissolves under anthropic reasoning. The second does not. The rare Earth hypothesis. Before the Kepler telescope, many scientists hoped the absence of alien signals was just a detection problem. Maybe intelligent life is common, but radio-loud civilizations are rare, or transient, or broadcasting on frequencies we have not checked. After Kepler, a different set of scientists began arguing for something more radical. The rare Earth hypothesis, developed primarily by paleontologist Peter Ward and astronomer Joe Kirschvink, suggests that the conditions required for complex multicellular life, let alone intelligent life, are so specific that Earth might be genuinely unusual in the observable universe. The argument is detailed and somewhat technical, but the core of it is this: Earth is not just a habitable planet. It is an extraordinarily well-suited planet, in ways that seem unlikely to be replicated often. The Moon is unusually large relative to Earth, and this stabilizes Earth's axial tilt. Without the Moon, Earth's tilt would wobble chaotically over millions of years, creating dramatic climate swings that might prevent the development of complex ecosystems. We have the Moon because of a specific, improbable collision event early in the solar system's history. Jupiter sits in an orbit that causes it to act as a shield, deflecting many of the large asteroids and comets that would otherwise bombard the inner solar system much more frequently. Frequent large impacts would periodically reset evolution, preventing the accumulation of complexity. We might not be here without Jupiter's gravitational protection. Earth lies in the galactic habitable zone, far enough from the dense, violent galactic center to avoid excessive radiation and gravitational disruption, but in a region rich enough in heavy elements from previous generations of stars to build rocky planets and biochemistry. Many parts of the galaxy do not meet both conditions simultaneously. The Sun is unusually quiet for its type. Many Sun-like stars flare violently, blasting their inner planets with radiation that would strip atmospheres and sterilize surfaces. The Sun's relative stability has given Earth billions of years of relatively benign conditions. Plate tectonics, which on Earth recycles carbon and drives chemical cycles that stabilize climate over long timescales, requires a planet with specific internal heat dynamics, specific water content, specific mineral composition. It is not clear how common plate tectonics is. Taken individually, each of these factors seems like it might not be essential. But if complex life requires most or all of them together, the probability of a planet meeting all the conditions simultaneously might be very small indeed. Maybe one in a galaxy. Maybe one in the observable universe. The rare Earth hypothesis has been criticized and partially rebutted, but it remains influential. It shifts the most probable location of the great filter from the future to the deep past, from the emergence of technology to the emergence of complex life. If it is right, we are not approaching a cliff. We have already survived the impossible. I find myself unable to fully accept rare Earth, because it requires arguing from our ignorance. We have not studied enough planetary systems, do not understand enough about the origins of life, to be confident that our particular combination of lucky circumstances is truly necessary rather than just one of many roads to complexity. But I cannot dismiss it either. The history of science has repeatedly shown that what seems like a general rule is sometimes a very specific coincidence. Earth might be a place that got almost everything right, in a galaxy full of places that got most things wrong. The silence would then be the natural result. The principle of mediocrity, challenged. What the children will ask. I want to end this section by thinking about the future, specifically about what the next generation will make of all this. The children being born today will live through a period of extraordinary discovery. The Vera Rubin Observatory will survey the solar system in unprecedented depth. Future space telescopes will be able to directly image the atmospheres of Earth-like exoplanets and look for biosignatures, oxygen, methane, the specific chemical disequilibria that indicate life. Within a few decades, we will likely have a statistically significant answer to whether life is common or rare in the cosmos. If biosignatures are found, if we detect life on multiple worlds within our galactic neighborhood, the Fermi paradox becomes a different kind of problem. Life would be common, which means the filter must be either the development of intelligence or the survival of technological civilization. And if it is the latter, the warning could not be more clear. If biosignatures are found nowhere, if the atmospheres of dozens of Earth-like planets show only the dead chemistry of an uninhabited world, then the rare Earth hypothesis gains enormous traction. We would be faced with powerful evidence that life itself is vanishingly rare, and that our existence is among the most improbable things that has ever occurred in the history of the cosmos. Either outcome is extraordinary. Either would reshape how we understand ourselves and our responsibilities. The children will ask us what we did when we knew the stakes. They will ask whether we took the Fermi paradox seriously as more than an intellectual curiosity. Whether we treated the management of existential risk as the most important problem of our time. Whether we built institutions capable of thinking at civilizational timescales. Whether we left them a world that had a future. I do not know what we will tell them. I know what I hope we will tell them. I hope we will say, we saw it. We understood what was at stake. We disagreed, sometimes bitterly, and we made mistakes, sometimes serious ones. But we kept working. We kept the lights on. We left you a civilization that is still trying, still asking the question, still reaching out into the silence. We hope you find the answer. We hope it is a good one. The final silence. I want to come back to the experience of actually listening to the silence. Not the abstract scientific fact of it, but the phenomenological experience. What it is like to actually sit with the question and feel its weight. There is a place, a particular kind of mental space, you can reach when you think about the Fermi paradox long enough and seriously enough. It is not comfortable. It is not exactly frightening. It is something more like awe, in the older, truer sense of the word, which includes both wonder and dread. You are sitting on a small rock, circling an ordinary star, in an unremarkable corner of one of 2 trillion galaxies. The universe around you has been running its processes for almost 14 billion years. Stars have been born and died. Worlds have formed and been destroyed. Complexity has assembled and dispersed. All of this has been happening, continuously, in the vast dark, for almost incomprehensible stretches of time. And for all of that time, as far as we can tell, nothing has looked back. No telescope has turned our way from across the void. No signal has been received. No artifact has arrived with a return address. Just us. Just this. In that moment, 2 feelings compete. The first is vertigo. The sense of enormous, hollow space pressing in from all directions. The second is something harder to name. A kind of clarity. The recognition that this fragile, improbable situation is not a reason for nihilism but the exact opposite. If consciousness is this rare, if the capacity to notice the universe is this improbable, then every moment of noticing is incalculably valuable. Every time you step outside and look up and feel something, wonder, curiosity, joy, even just the mild pleasure of a clear night, you are doing something that may never have been done before anywhere in the observable universe. Or, if it has been done, it was done by beings who are gone, leaving behind only cold silence and maybe some tumbling object drifting through the dark. The silence is not empty. It is full of everything that did not quite make it. Full of worlds that tried and failed, of processes that stopped just short, of probability that came up just barely wrong in one crucial step. We got the crucial steps right, or right enough, and here we are. And what we do with that fact is the only question that ultimately matters. Do we treat it as luck, something to exploit for our immediate benefit? Do we treat it as burden, something too heavy to carry consciously? Or do we treat it as responsibility, something that comes with obligations we may not have asked for but cannot ethically decline? The Fermi paradox does not tell you which to choose. It just makes the choice feel more serious. It gives weight to a question that is always present but easy to ignore. What kind of civilization do we want to be? Because the silence out there is partly a reflection of the choices that others made, or failed to make. And the future silence, or noise, or music of this galaxy will partly be a reflection of the choices we make now. We are writing a page in a book that may have very few other pages. We should write it carefully. The question is not only where everybody else is. The question is who we are going to be while they are absent. And whether, when the next civilization points their equivalent of a radio telescope at the coordinates where our sun used to be, they will find silence or something worth hearing. That is the Fermi paradox, fully unpacked. Simple question. Devastating implications. Where is everybody? Right here, trying to answer. The technological dimension. Let me talk about technology, because it is impossible to discuss the Fermi paradox seriously without grappling with what technology does to civilizations. Technology is, in the Fermi paradox framework, both the salvation and the threat. It is what would allow a civilization to become detectable across interstellar distances, and it is also, plausibly, what ends civilizations before they get the chance. We are, by historical standards, a very young technological civilization. The Industrial Revolution is only about 250 years old. Nuclear technology is less than a century old. The internet is younger than most people reading this. Artificial intelligence, as a serious transformative technology rather than a theoretical concept, has become genuinely powerful in only the last decade. The pace of this acceleration is staggering. It took Homo sapiens approximately 200,000 years to go from sharpened stones to agriculture. It took 10,000 more years to go from agriculture to steam engines. 150 years from steam to nuclear weapons. 60 years from nuclear weapons to smartphones. 10 years from smartphones to systems capable of passing professional examinations, generating art indistinguishable from human work, and reasoning through complex multi-step problems. Where does this curve go? Nobody knows. That is the honest answer. The people building these systems, the people thinking hardest about them, do not know. There are serious researchers who believe we are within decades of artificial general intelligence, systems that can perform any cognitive task a human can. There are others who think that timeline is wildly optimistic and that we are much further away than the hype suggests. Both positions are held by people who have spent their entire professional lives on this problem, and they disagree sharply. What is clear is that the development of advanced artificial intelligence represents a phase transition in the history of technology. Everything before AI was a tool that amplified human physical or cognitive capacity in specific domains. AI, at sufficient capability, would amplify cognitive capacity generally. It would not be a better hammer or a faster calculator. It would be something qualitatively new, a system that can do the thing that humans do uniquely well, which is general-purpose reasoning. The implications of that for the Fermi paradox are significant. An AI with general-purpose reasoning capability could, in principle, accelerate the development of every other technology. It could run science faster, design better materials, solve engineering problems that have stumped humans for generations. A civilization with advanced AI would develop at a rate that makes the last century of human progress look glacial. Such a civilization would become detectable from across the galaxy, or destroy itself, much faster than one without AI. The Fermi paradox window I discussed earlier would get much shorter. The gap between just starting to use fire and building a Dyson sphere or destroying everything would shrink dramatically. This is either very good news or very bad news, and which one it is depends entirely on whether the AI development goes well or poorly. If it goes well, civilizations might ascend to Type 2 or Type 3 status in centuries rather than millennia. If it goes poorly, they might eliminate themselves in decades. The fact that we see no Type 2 or Type 3 civilizations might then be evidence that AI development tends to go poorly. That the period between inventing general AI and ending civilization is very short. That the filter is not nuclear weapons or engineered pathogens but the thing that seems, right now, like our greatest hope, the creation of artificial minds. I want to be careful here not to be catastrophist. I am not saying AI will definitely destroy us. I am saying that the Fermi paradox provides a specific, sobering context for thinking about AI risk. If we are asking why the galaxy is empty, and if AI development is a near-universal stage in the history of technological civilizations, and if the galaxy is empty, then we have some probabilistic reason to worry about how that stage tends to go. This should inform how seriously we take AI safety research. Not as an esoteric technical concern for specialists, but as something potentially as important as any other existential risk our civilization faces. Maybe more important, given the speed at which it is developing. The contact problem. Assuming, for a moment, that there are other technological civilizations out there, either now or in the recent past, what would actual contact look like? And would it be a good thing? The conventional picture of first contact, inherited from science fiction, tends to fall into one of two extremes. Either the aliens are benevolent and wise and their arrival transforms humanity into something better, or they are hostile and their arrival initiates a war of extermination. Both scenarios are driven by a kind of anthropomorphism, by projecting human psychology onto beings whose minds might be nothing like ours. Real contact, if it ever happened, would probably be stranger and more complicated than either scenario. To begin with, contact would almost certainly not be a ship appearing in orbit. The distances are too great and the energy requirements too enormous for physical travel to be the first mode of contact for most civilizations. The first contact would be electromagnetic, a signal. And signals take time to cross the vast distances involved. If we received a signal tomorrow from a civilization around a star 100 light-years away, we would be hearing something that was sent 100 years ago. The civilization that sent it might have changed dramatically in the intervening century. They might be gone entirely. Any response we sent would take another 100 years to reach them, and 100 years after that for their reply to come back. Contact would be a conversation in geological time. This is not like anything we have experienced. Human communication, even across historical distances, has been fast enough that both sides can treat it as real-time interaction. Contact across interstellar distances would be nothing like that. It would be more like archaeology, studying a distant civilization through the artifacts it has sent across time, knowing that whatever you learn is already history. What would we learn from such a message? That depends entirely on what they chose to send, and that is not something we can predict. A civilization that has survived long enough to develop interstellar communication has clearly solved some of the problems we are struggling with. Their choices about what to broadcast would reflect values and priorities shaped by that survival. We might find the message uplifting, or baffling, or frightening, or all three simultaneously. What should we send back? This is a question that the Medi debate revolves around, and it is genuinely difficult. What do you say to a mind that might be completely alien? What is universal enough to communicate meaning across species boundaries? Mathematics seems like a starting point. Physical constants. The periodic table. But beyond the basics, how do you convey anything that matters about what it is like to be human? There is something poignant about this problem. The things that matter most about us, the things we would most want to share with any civilization that existed, are precisely the things that are hardest to translate. Not our science, not our mathematics, not the size of our planet or the composition of our atmosphere. What would be hardest to transmit is the subjective experience of being here. The feeling of a warm afternoon. The loss of someone you love. The specific quality of the light at dusk. The sound of music. These are not data that compress into radio waves. They are not universal. They are deeply, stubbornly particular. And if intelligence across the universe tends to produce particularity, then the silence might partly reflect the difficulty of communicating the things that matter most. We might be capable of confirming each other's existence without being capable of understanding each other at any deep level. That would be a strange and melancholy form of contact. Hello, we exist. Yes, so do we. Beyond that, nothing. Or perhaps alien minds are strange in exactly the ways that make contact not just difficult but impossible. Perhaps the category of intelligence that we represent, biological, embodied, emotionally driven, is just one tiny corner of the space of possible minds, and most of the others are so different from us that our concepts, our questions, our desires do not translate at all. This is the hard version of the contact problem. Not the logistics of sending and receiving signals across vast distances, but the deeper question of whether minds can meaningfully meet across radical differences of origin and design. Whether there is enough common ground for any real exchange to occur. I hope there is. But I am not sure. The meaning of being first. Let me return to what I find to be the most extraordinary possibility in the Fermi paradox, that we might genuinely be first. Not first in our solar system, necessarily. Not first in some narrow local sense. First in the galaxy. First in the observable universe. The initial emergence of intelligence in a cosmos that has been running its processes for almost 14 billion years. Think about what that means in the largest possible frame. The universe began, as best we can tell, as a hot, dense, featureless soup of fundamental particles. Over time, gravity pulled those particles into stars. Those stars cooked up heavier elements in their cores. They died, scattering those elements into space. New stars formed from the enriched gas, and around some of those stars, planets coalesced. On some of those planets, the chemistry of carbon, water, and energy produced self-replicating molecules. Those molecules evolved, over immense stretches of time, into cells, into organisms, into ecosystems, into minds. And now, for possibly the first time in the history of the cosmos, a part of the universe is looking at the rest of it and trying to understand it. Not just reacting to it, not just using it for energy, but actually forming models of it, building theories about it, asking questions that have no immediate practical value but that are asked anyway out of pure curiosity. We are the universe become aware of itself. This phrase has become almost a cliché, but its truth does not diminish with repetition. It is extraordinary. It is unprecedented. It might be unique. And if it is unique, if we are the first minds the cosmos has produced, then the responsibility is almost unbearably large. Because we are not just responsible for ourselves. We are responsible for the possibility of mind itself. If we fail, if we destroy ourselves, the universe does not necessarily try again. The cosmic experiment in consciousness might be over. That is a thought I can hold for only a few seconds before it becomes too large to sit with. But I think it needs to be held, even briefly. Because it changes the moral stakes of everything. The decision to build a nuclear weapon, the decision to release an engineered pathogen, the decision to deploy an AI system we do not fully understand, the decision to ignore the warning signs of civilizational collapse, every one of these decisions is now loaded with cosmic significance that it would not carry if we were certain that the universe was full of other minds who would carry on after us. We might be the only chance the universe has to know itself. We should act accordingly. What this means for right now. I want to come down from the cosmic heights for a moment and talk about what the Fermi paradox means for decisions you might make this week, this month, this year. Because I think the lesson of the Fermi paradox is not despair. It is urgency. It means, take the long view. Think about consequences that extend beyond the next quarterly report, the next election cycle, the next decade. The universe operates on timescales that dwarf human history, but human choices made in human time can have consequences that extend to cosmic timescales. A civilization that deploys a self-replicating technology it cannot control might not get a second chance. A civilization that destroys its climate might not recover quickly enough to escape its own planet before the window closes. It means, value intelligence. Genuinely value it, not instrumentally, not as a means to economic production, but as the thing that the universe has been trying to produce for 14 billion years. Every child who does not get an adequate education, every scientist whose funding is cut for short-term budget reasons, every institution of learning that is defunded, represents a loss that goes beyond the individual and the local. Intelligence is the universe's most precious product. Treating it as optional is a cosmic mistake. It means, take existential risks seriously. Not as political talking points, not as distant abstractions, but as the central organizing challenge of our civilization. The work being done on AI alignment, on biosecurity, on nuclear risk reduction, on climate resilience, is not secondary to the normal business of civilization. It is the most important business of civilization. Because none of the other business matters if we do not survive it. It means, cooperate across differences. The Fermi paradox suggests that civilizations which destroy themselves do so, often through internal conflict. War, inequality, tribalism, the failure to act collectively on shared threats. If we are to cross the filter, we have to do it together. Every institution that helps humans cooperate across national, cultural, and ideological lines, every international treaty, every diplomatic engagement, every trade relationship, every scientific collaboration, is a small contribution to the project of not ending up like the others who came before and failed. It means, hold this planet gently. We have one planet that we know for certain can support intelligent life. We should treat it as the irreplaceable miracle it is. Not because the Earth is sentimentally meaningful, though it is, but because the conditions that allow complex intelligent life are so hard to find that we should not take them for granted. And finally, it means, look up. Not just literally, though that too. Maintain the capacity for wonder. Keep asking the question. Keep listening. Keep building better telescopes and sending better probes and thinking harder about the silence. Because the universe is 13.8 billion years old and we are very new here, and the best thing we can do with whatever time we have is use it well. The silence is enormous. The stakes are real. And we are still here. That is, depending on how you look at it, the most remarkable thing that has ever happened. Let's make it mean something. The question that remains. After all of this, after the Drake equation and the Kardashev scale and the dark forest and the great filter and the transcendence and the brief window and the rare earth and the simulation and all the rest, the question is still there. Where is everybody? We do not know. But we are still asking. And maybe that is the most important thing. Not the answer, but the asking. The insistence on looking into the silence and demanding it explain itself. The refusal to be satisfied with not knowing. The combination of humility, because we recognize how much we do not understand, and ambition, because we are still trying to understand it. That combination, humility and ambition, curiosity and rigor, wonder and discipline, is what has produced everything we know about the universe. It is what produced the telescopes we built to look for the signal. It is what produced the theory of the Fermi paradox itself. It is, in some sense, what we are. So the silence continues. And we continue. Listening, looking, thinking, arguing, building, reaching. Because that is what it means to be here. That is what it means to be the part of the universe that asks questions. And somewhere, in the dark, the universe waits for us to figure it out. The firefly flickers. Still here. Still burning. Still asking. The observatory at the edge of everything. I want to describe a thought experiment that I return to often, because I think it crystallizes everything the Fermi paradox is actually about. Imagine you are an astronomer. Not a human astronomer operating with human instruments and human assumptions. Imagine you are an astronomer with truly advanced technology, capable of observing every star system in the observable universe simultaneously, at every wavelength, across any timescale you choose. You spend the first billion years of the universe's existence just watching. Nothing interesting happens. Hot plasma cools. Hydrogen clouds begin to collapse under gravity. The first stars ignite, burn bright, and explode. Heavy elements scatter into the void. second-generation stars form around them. You spend the next few billion years watching galaxies assemble. Stars and planets multiplying across the cosmos. The universe getting increasingly complex, increasingly structured. But still, no mind. No awareness. No one watching back. At a certain point, in a certain galaxy, in a certain arm, in a certain unremarkable solar system, something changes. On the third planet from a yellow dwarf star, molecules that can copy themselves begin to compete for resources. Over 4 billion years, that competition drives increasing complexity. Eventually, after enormous suffering and enormous beauty, after extinctions and radiations and a slow accretion of complexity upon complexity, a species emerges that is capable of asking what it is. Now, in your hypothetical observation of the entire universe, you face a strange question. You have been watching for 13.8 billion years. How many other places in the cosmos have produced something similar? If the Fermi paradox is pointing us toward the truth, the honest answer might be, not many. Maybe none, until now. Maybe this yellow dwarf star's third planet is the first place in the observable universe where something complex enough to notice the universe exists. Sit with that. Really sit with it. Every philosophical tradition, every poem ever written, every scientific discovery, every act of kindness or cruelty or art or music, every experience of love or loss or wonder or boredom, every dream and every nightmare, every moment of consciousness that has ever occurred in the known universe might have occurred on one small world. And from your hypothetical observatory, looking at the vast dark, you would see a single, tiny light. One planet. One species. Making mistakes, waging wars, building things, destroying things, asking questions. That is us. The responsibility argument. Once you take that image seriously, the ethical implications are unavoidable. We are accustomed to thinking about ethics in terms of human well-being, or at most, the well-being of sentient life on Earth. Animal welfare ethics expands the circle to include other minds. Environmental ethics expands it further to include ecosystems and future generations. But the Fermi paradox suggests a fourth expansion, cosmic ethics. Not just what is good for humans, not just what is good for sentient life on Earth, not just what is good for future generations, but what is good for the project of intelligence in the universe. If we are the first or only minds the universe has produced, then our survival and flourishing has a weight that goes beyond any ordinary ethical calculus. It is not just us that we would be destroying if we failed. It would be the universe's only experiment in self-knowledge. I recognize that this sounds grandiose. I recognize that cosmic ethics is not a framework with much institutional traction. But I think the logic is sound, and I think it changes things. Specifically, it changes how we think about risk. Normal risk management balances the probability of harm against its magnitude and against the cost of prevention. Existential risk is categorically different. An existential threat, one that would destroy human civilization or human potential permanently, is not just a large risk. It is in a different category. Because you only get one chance. There is no recovery from extinction. There is no second attempt after civilizational collapse of sufficient depth. This is why people who think seriously about existential risk tend to be willing to pay enormous costs in terms of reduced current welfare to marginally reduce the probability of existential catastrophe. They are not being alarmist. They are doing correct expected value calculations that take seriously the possibility of a very bad outcome from which there is no recovery. The Fermi paradox makes this even more stark. If we are alone, then losing us is not just losing us. It is losing everything that intelligent life in this part of the universe could ever become. Every star we might visit. Every civilization we might build. Every being that might one day exist and think and love and wonder. It is losing the universe's only reader. That is not a normal risk. That is the maximum possible downside. Which is why I think the Fermi paradox has direct bearing on how we allocate attention and resources. We are currently spending the vast majority of our civilizational energy on things that matter on a human scale: the economy, politics, entertainment, social conflict. These things matter. But we are spending a very small fraction of our energy on the things that matter on a cosmic scale: existential risk reduction, long-term civilizational planning, the actual project of making sure that the firefly's light does not go out. That allocation seems wrong, given what the Fermi paradox implies about our situation. The search that never ends. One of the things I love about SETI, even in its current form, even with all its failures and frustrations, is that it is an expression of something deeply human and deeply admirable: the refusal to accept not knowing. We have been listening for signals for over 60 years. We have found nothing. Reasonable people could be excused for concluding that the search is hopeless, that we are wasting resources, that we should direct attention elsewhere. But the people running SETI do not feel that way. And I think they are right, not just because the question is important, but because the act of searching is itself valuable. Here is what I mean. The search for extraterrestrial intelligence forces us to think clearly about what we are. About what intelligence is, what it requires, how it arises, how it persists. It forces us to examine our assumptions about what is universal versus what is particular to us. It forces us to think about the long run, about what becomes of civilizations over centuries and millennia and longer. These are not abstract philosophical exercises. They are directly relevant to understanding our own situation and our own future. In trying to figure out where everyone else is, we learn things about ourselves that we could not have learned by just looking inward. The search also keeps alive a certain quality of attention: the willingness to be surprised, the readiness to receive information that overturns our assumptions, the humility to accept that the universe might not conform to our expectations. That quality of attention is one of the most valuable things science produces, and it has applications far beyond the specific question of alien civilizations. A civilization that has learned to genuinely listen is better equipped for all kinds of discovery. So the search continues. Every night, somewhere, radio telescopes are sweeping the sky. Optical telescopes are looking for laser pulses. Infrared surveys are checking for Dyson structures. The data is being analyzed, the patterns are being checked, the frequency space is being systematically eliminated. And every night, nothing. The silence continues. But also every night, we are here. Still asking. still listening, still insisting on taking the question seriously. And there is something in that insistence, something in the combination of improbability and persistence, that might itself be the most meaningful thing about us. We are the part of the universe that refuses to stop asking why it is so quiet. The distance between the stars. Let me close with something about physics, because the physics of the silence matters as much as the philosophy. The nearest star to our Sun is Proxima Centauri, about 4.2 light-years away. At the speed of our fastest spacecraft, the New Horizons probe, it would take about 80,000 years to reach it. That is longer than anatomically modern humans have existed. It is about 8 times longer than all of recorded human history. If Proxima Centauri had a habitable planet with a civilization equivalent to ours, we could not travel there. Not with anything we currently have. Not with anything we can envision building within the next century. The distances are simply too great for chemical rockets. To make interstellar travel practical requires either speeds that are a significant fraction of the speed of light, which requires energy inputs many orders of magnitude beyond anything we can currently produce, or methods of propulsion that do not yet exist theoretically, let alone practically. Nuclear propulsion might get us to a few percent of the speed of light. Laser-pushed sails, the breakthrough starshot concept, might get us to 20%. At 20% of the speed of light, Proxima Centauri is still a 20-year journey. And Proxima is right next door, cosmically speaking. The galaxy is 100,000 light-years across. The distance to the center is 26,000 light-years. Other galaxies are millions to billions of light-years away. These are not distances that biology can cross, at least not as we understand biology. These are not distances that civilization, as we understand civilization, can cross and remain coherent. This is part of what makes the silence so puzzling. Even if contact were desirable, even if there were a civilization only 100 light-years away that desperately wanted to know we existed, the constraints of physics make rapid communication essentially impossible. They would be speaking to us across centuries. And this is part of what makes the zoo hypothesis so implausible. For a galactic community to agree on a prime directive and enforce it for millions of years, they would need to communicate across distances where the light travel time alone is thousands of years. Maintaining coherent policy across those timescales and those distances strains credulity. The physics of light-speed communication shapes what any interstellar civilization would be like in ways we tend not to fully appreciate. There would be no galactic empire, no unified governing structure, no real-time coordination across star systems. Any civilization that spread across multiple star systems would necessarily fragment into essentially independent entities, each evolving separately, each developing its own culture and values and perhaps its own version of the original civilization's goals. The silence, in this light, might reflect not just the rarity of intelligence, but the physics-imposed isolation of intelligence. Even a universe full of civilizations might appear silent to each one, because the speed of light prevents the kind of rapid, repeated, unmistakable contact that would announce presence clearly. By the time any signal reaches us, the civilization that sent it has had centuries or millennia to change. We are separated not just by distance but by time, and the two separations compound each other in ways that make genuine contact enormously difficult even if intelligence is common. This does not dissolve the Fermi paradox. Even with these constraints, a sufficiently advanced civilization could make itself visible from across the galaxy. Dyson structures do not require real-time communication. Self-replicating probes, once launched, spread without further instruction. The silence remains unexplained, but it adds nuance. The universe of minds, if it exists, would not look like a party to which we have not been invited. It would look more like a collection of isolated islands, each developing in ignorance of the others, shouting across distances that none of them can reliably cross in biological time. In that universe, the silence might be simply the physics of the situation. Not malice, not filter, not transcendence. Just the unyielding speed of light, ensuring that the universe's minds can never quite catch up with each other. And in that universe, we are still one of those islands. Still sending signals that will take centuries to arrive. Still waiting for signals that might have been sent centuries before our grandparents were born. Still here. Still trying. Still asking. This is perhaps the most human thing about us, the insistence on reaching out across distances that physics makes nearly uncrossable, to minds that might not exist, with a message that might never arrive. It is irrational by certain measures. It is beautiful by others. And it is what we do. Because we are the part of the universe that cannot stop asking. The last light of the last star is still billions of years away. The universe's story has barely begun. And we have already started telling it. Wherever you are. However long we last. We were here. We asked the question. We listened for the answer. And we did not stop. The last word on silence. There is something I have been holding back, something I want to say plainly at the end of all this. The Fermi paradox changed me. Not dramatically, not overnight, but gradually, the way all the most important changes happen. Somewhere in the years of thinking about it, of reading the papers and the books and the arguments and the counter-arguments, something shifted in how I experience being alive. I walk outside at night differently than I used to. When I look up at the stars, I do not see the friendly, familiar sky of childhood mythology or the abstract data of physics textbooks. I see the actual physical reality of the situation, an enormous, ancient, possibly empty cosmos in which we are one small, fragile, improbable, aware thing. And that does something to you, if you let it. It makes you less casual about existence. Less willing to take for granted the fact of consciousness, the fact of this moment, the fact of being a mind that can look at the universe and say, I see you. The silence is not comfortable. But I have stopped wanting it to be comfortable. Because the discomfort is the truth, and the truth, however uncomfortable, is better than the comfortable lie. We might be alone. That would be the most important fact ever discovered. We might not be alone, and whoever else is out there might be dangerous, or dead, or transcended beyond our ability to recognize. Each of those would also be enormously important. Or we might, eventually, find genuine peers. Minds that emerged independently, that developed differently, that have solved some of the problems we are struggling with, and that are willing and able to share what they know. That would be the best possible discovery. I do not know which of these is true. I do not think anyone does, yet. But I know that the question matters. I know that how we approach it, how much attention we give it, how seriously we take the implications, is itself a kind of answer. A civilization that treats the Fermi paradox as a serious, urgent, civilization-defining question is a civilization that is more likely to become the exception. More likely to survive the filter, whatever it turns out to be. A civilization that treats it as a curiosity, a fun thought experiment for a rainy afternoon and then forgets about it, is a civilization that has not understood its own situation. I want us to understand our own situation. I want us to be the exception. I want us to be, for some distant civilization in some distant future, the answer to their version of the Fermi paradox. The signal they finally receive, after their own long silence, that confirms, we are not alone. Someone else made it. Someone else crossed the filter. Someone else decided that existence was worth protecting, that intelligence was worth cultivating, that the universe's capacity for self-knowledge was worth preserving at enormous cost and effort and care. That is the goal. That is what the silence is asking of us. Not a small goal. Not an easy one. But the only one that is proportionate to the situation. The stars are old. The silence is deep. And we are here, briefly, awake. Let's make it count. A note on the sources of wonder. Before I fully let you go, I want to mention something about where this kind of thinking comes from, because I think it matters for how you engage with it going forward. The Fermi paradox is not a single discovery. It is not a fact you can look up in a textbook and check off as known. It is a question, and questions have to be lived with, returned to, turned over, held against the light at different angles over time. Some of the most interesting thinking about it has come from physicists and astronomers, Hart, Tipler, Brin, Webb, Davies. Some has come from philosophers thinking about probability and anthropic reasoning. Some, unexpectedly, has come from science fiction writers, Liu Cixin chief among them, who turned the dark forest theory into a novel that has made more people think carefully about strategic uncertainty in interstellar contact than any academic paper ever could. And some of the best thinking has happened in ordinary conversation, in the kind of late-night discussions where someone says, "But wait, if there are really 400 billion stars in our galaxy, why aren't we already surrounded by alien signals?" And everyone falls quiet because they realize they do not have a good answer. That question, taken seriously, leads everywhere. To the great filter and its terrifying implications. To the structure of the Drake equation and the enormous uncertainty at every step. To the Kardashev scale and what a Type 3 civilization would actually look like. To the physics of interstellar travel and the improbable difficulty of crossing even the nearest distances. To the evolution of intelligence and the question of whether it is inevitable or accidental. To the possibility of simulation and what it would mean if we were inside one. To the nature of consciousness and whether it requires biology. The Fermi paradox is a thread, and pulling on it unravels the whole universe. Which is why it is worth pulling. Not because you will reach a conclusion. Not because the puzzle will resolve into a neat answer. But because the pulling is how you develop the kind of mind that can live in a universe where the deepest questions remain open, where the stakes are enormous, and where the only reasonable response is to keep looking, keep asking, keep caring about the truth. That kind of mind is, I think, what the universe has been building toward, if it has been building toward anything. And that kind of mind is what we need to be, now, at this particular moment in the long and uncertain history of intelligence on this planet. The silence is not a wall. It is the universe, waiting to see what we do next. What will we do next? That is entirely, uncomfortably, gloriously up to us.